Okay. So couple of more classes to go. The last class we switched from Pozar to Cheng. We were looking at single stub, double stub, impedance matching and tuning. So Cheng has actually examples which have more simplified steps. Pozar also has as examples. So I've covered examples from Cheng. Um, you can look at the examples from Pozar. In by the next week, I am planning to give a few more assignments, just some selected questions from the textbook, which you can go through. The questions will be from Pozar, and the solutions are also available. But in case if you feel like something needs to be discussed, we can do that. Okay. So we started with module 7 in the last class, microwave resonators. We looked at series RLC circuit. So essentially, the idea is that when we design microwave circuits, so we do that with distributed elements, right? So, but all these distributed elements can be simplified to form an RLC circuit. It could be a parallel RLC circuit, series RLC circuit, or some mixed form of them. Basically, we can form simplified equivalent models, and if we know the uh, series and parallel RLC circuits, we can use that information to basically understand the working and designing of microwave resonators using distributed elements as well. So today we'll finish with module 7, and the next class will start with module 8. So I have put this extra class like on a very short notice. So so whoever is not able to attend this class, they can go through the recordings. Okay, so in the last class, we finished with the double stub matching. Maybe we'll quickly revise this now. And we have started with series resonant circuits. We'll do revision of this and then start with parallel resonant circuits. So essentially, the double stub matching that we discussed this in detail. So just to give you a quick idea, that double stub matching is used when we cannot use a single stub matching, because the single stub's location, this as in single stub we have this d distance, right, where the stub has to be put. But if that distance comes out to be at a place which is inconvenient for us to fabricate or put it in the circuit, we use a double stub matching, because then what we do is we add a stub at the load, and when we do that, we are basically modifying the load impedance over here. And when we modify this load impedance over here, this using that, we can modify this d distance such that we can attain a distance where we can easily put this stub over here. So the second stub will be will be convenient to us. Like we can find out a location which is convenient to us where we can put this stub. So we're modifying the load impedance using one stub, and so that we can obtain this distance where we can conveniently put the other stub. There is also a double stub matching where you can put this stub before the load. So you will have two distances, but that will again become more complex than this double stub matching. And Poser has some text written on this, but essentially that becomes too complex as also for this course as well. So you can go through papers or other textbooks which have more details in this if you're interested, but this should suffice for our purposes now. So we looked at the equations for double stub matching. That's what we are trying to do is we have this transmission line circuit over here, and we want to match it to this load impedance. And to do that, the first goal is that the input admittance at this particular point should be equal to the equivalent admittances provided by YB and YSB. And that is the goal. And this Y input impedance, looking at this port over here, should be equal to the inverse of 1 by R naught. So this is the goal, and on doing that, we can basically do more formulations. And over here, what we do is we try to add this stub over here and modify this load impedance, and find out a distance d naught such that at this particular point, the YB has the real part equal to 1, and whatever the imaginary part is then compensated by this stub over here. So this is the idea. And then we discussed the steps in detail. These they're listed over here, and we looked at one example as well. So we went through this example. It took quite a lot of time in the last class. So maybe so I'll skip this now because again going through the steps will take a lot of time. And then we started with microwave resonators. So maybe I can pause over here, and if you have any questions at any of any of these steps, so they're marked from 1 to 7 over here. We can discuss that, or else we can proceed with the class. So I'll just pause over here just in case if you have any questions. Okay, so the example is also present in Cheng, so you can look at that as well. So I believe the steps are quite clear, and this will take time for things to sink in. But for an exam perspective, I think the best thing that you can do, which I also did, was remember the steps. Because this problem is very straightforward, that you have two stubs and you have to match a load to uh, uh, um, the transmission line, and the steps laid out are very like precise, and if you do that, you'll get the impedance matching. And when you solve a few questions, and then you get the idea of actually what is going on. So I have tried to give you the idea in brief, that adding one stub at the load and to modify the load impedance so that we can modify the d naught distance between the two stubs, that is the idea. Okay, so we'll just quickly go through the series resonant circuit as well. So the resonators are essentially used for a number of applications, like filters, oscillators, frequency meters, tuned amplifier. So these involve resonator circuits. So and to know their how they work, we should know a series and parallel RLC resonant circuits. So we'll cover those, and we'll also look at transmission line resonators, for example, and we'll show how knowing the series and parallel RLC circuit gives us the information to like model transmission line resonators. And then you can look at more examples. Podzar has examples on waveguide resonators, dielectric resonators. So for now, this is sufficient. If you want to go into depth for this particular topic, you can refer to the Podzar. But essentially, the series and parallel should suffice for the syllabus. Okay, so this is the series RLC circuit shown over here. So very standard, very simple circuit, and what we are saying that is that we could have a circuit which can be again simplified to form a circuit like this. And once we have simplified a circuit to its RL and C components, we can write the input impedance looking from the source as Zn equals to R plus j omega L minus j 1 by omega c, or plus 1 by j omega c, whatever is comfortable with you. And then we can also write the power delivered to the resonator. So this entire circuit is using up some power, so which can be given as half Vi conjugate. And we can also write in terms of the input impedance, Zin. And this is the power input power for this circuit. If you look closely, the half I square R term is the power dissipated by the resistor. So we can write it as P loss, and half I square j omega L is like this particular term is essentially can be simplified to this is in close relation with the average magnetic energy stored by the inductor. So omega this Wm is which can be written as half I square L is the magnetic energy stored in the inductor, and similarly for the capacitor is given by 1 by 4 I square 1 by omega square C, or we are writing this Vc as I square by omega yeah I square by omega square. So this is basically the voltage across the capacitor over here. This is Vc is across the capacitor, and the complex power can be given as the total power plus this power across the loss through the resistor, and 2j omega Wm minus Wm. So this comes from the Poynting theorem, right? So if you recall, the Poynting theorem gives us a formula like this. And the input impedance now we can write in terms of the input power as 2 pi n by I square, and we can substitute the input power by this formula over here. So which we just derived just above. Now, so summarizing, I've summarized this steps over here. So the input power can be written by the Poynting theorem like this, and we have the loss, power loss through the resistor, the energy in the inductor and capacitor, and the input impedance formula over here. Now, the resonance will occur when this omega m becomes equal, sorry, Wm becomes equal to We, and at this condition, we uh, we have the input impedance equals to power loss through the resistor by half I square, and this is equal to the resistance over here. So at the resonance, we have the input impedance equal to the resistance, and Wm equal to We. At this condition, we will have the resonance frequency. The frequency at which happening is we can denote it using omega naught, and omega naught can be found out by solving these two terms. When they are equated to 0, we get 1 upon root under LC. And we also defined one new term, or you might already be familiar with this, as the quality factor, which is the average energy stored divided by the energy loss. So the energy stored is Wm plus We, and the energy loss is P loss. So if you take their ratio, and this quality factor can be affected by the conductor loss, electric loss, radiation loss, and all these losses are accounted by the uh, this P loss term. So we went through their details, and we also looked at the term loaded and unloaded queue. So the loaded queue is when you have for the resonator circuit, if you have a load attached to it, the load will affect the Q quality factor of the circuit, and in that case, the quality factor of the circuit is called loaded Q. And if you're just looking at the quality factor of your resonator circuit, it is called the unloaded Q or Q naught. Now we also discussed the half power fractional bandwidth. So if you plot the input impedance with normalized frequency, you will observe that the plot looks something like this, and the at the half power, if you try to like if you mark this particular relationship, you will get. So the bandwidth is at the half power, and the half power is found out to be at when the input impedance is equals the square of the input impedance is equals to 2R square. And if you will just draw a line and you find out this bandwidth will turn out to be 1 upon Q naught. So bandwidth is equals to 1 upon Q naught, which is the unloaded quality factor. So this is what we covered. So, and any questions from here? Else we'll proceed with the parallel resonance circuits. So most things are actually what has you must have already covered at different courses from electrical engineering. So series and parallel RLC circuit is something that is also taught in network theory or basic electrical engineering courses. So most things are known, and then with our knowledge of input impedance and finding out Poynting factor, the power terms, we can derive all these results. The quality factor is the only new term, which is also covered in electrical engineering courses. So you might already be familiar with it. But anyways, we have covered through this, and when we look at the transmission and resonators, we'll get to know how the knowledge of series and parallel RLC circuit is useful while when we do formulations for distributed elements. Okay, so we'll proceed with the material that we are supposed to cover today. So a parallel RLC circuit looks something like this, where we have the resistor, inductor, and capacitor. The if you have a circuit whose equivalent circuit is drawn like this, then we will see we call it the parallel resonant circuit, and we can calculate the input impedance from looking from the source towards the resonance circuit as Z input as this particular uh, equation over here. So we're taking so these are in the each element is in parallel. So we calculate the impedances and just adding them their reciprocals and taking the inverse, we get this Z input impedance. So this is fairly straightforward. And the now we just substitute this value of input impedance in the same thing do the same thing as we did in the series resonant circuit, and we get the input power. So the input power is this vi square by z input, and zin is this whole thing minus 1. So this gets multiplied over here, and this is the input power. Now the again, the power dissipated by the resistor is same as we did in the series uh, case. And now the average electric energy is given by WE, which is same, and the average magnetic energy is given by WM, which is same. So if you notice, instead of using current, we're using voltage because current will be variable in each of these elements, but voltage will remain across same across them. So for consistency, we are using voltage terms instead of current terms. And again, using the same Pointing theorem, we write this equation over here, and we write the input impedance in terms of the input power. So this is all similar to what we did in the series resonant circuits. So any questions from here? So we are doing whatever was done for series resonant circuits. Okay. So we now have the power loss through the resistor as P loss V square by R, the magnetic energy as 1 by 4 V square by omega square L, and the uh, energy stored in the capacitor, electric energy stored in the capacitor as 1 by 4 V square by C. And the input impedance in terms of the input power, which where we have substituted the uh, equation for the input power as P from the Poynting theorem. Now, similarly, what we did for the series resonance series case, the resonance occurs at Wm equal to We, where so we are making the imaginary part of this input impedance equals to 0, and upon doing that, we see that the input impedance becomes equal to the resistance value over here, and the resonant frequency omega naught is found to be 1 upon root under LC, which is same as the series resonant case. So these two observations remain same even though the circuit has changed. The input impedance and the resonant frequency remains the same. And the one thing that this for like just to know that resonance in case of parallel RLC circuit is sometimes called anti-resonance. So and we do this because okay, we'll see one plot over here sometime. So the input impedance versus frequency plot, which is it is just the in like if you visually you can see it is upside down. So we'll see that. Before that, let's just look at the unloaded Q of this parallel resonant circuit, and this turns out to be omega naught RC and R by omega naught L. So yeah, so unloaded Q is given over here, and from this result we can see that the the quality factor for the parallel resonant circuit increases as R increases, while in case of the series resonant circuit, the quality factor decreased in case of the in when R increased. So just the opposite effect over here. And now near the resonance, the input impedance can be now simplified using this particular expression over here. So let me just put this over here. Yeah. So we have the input impedance looking like this, right? So we had calculated the input impedance for this parallel resonant circuit, and this the whole thing had this -1 term, and we have this solution like expression known to us. 1 by 1 plus x is equivalent to 1 minus x plus x square and other terms. So this comes from binomial expansion, if you can recall. So we are using this expression over here to simplify the input impedance term. Now, before doing that, okay, so there is one thing missing over here, maybe. So there should be this delta term over here. So we are substituting omega is equals to omega naught, and omega naught is the resonance frequency, uh, and delta omega is very small. But delta again over here as well. So delta omega is much smaller than omega naught. Okay. Yeah, so we're substituting omega over here, and delta omega is much smaller than omega naught. And after substituting this, we then simplify it more and more. And once we have achieved, so I'll let you do this math by yourself. So you should reach something like this. So this particular term over here is vanishing because delta omega is much smaller than omega naught square. Uh, yeah. So you'll achieve something a term like this, R by 1 plus 2j delta omega RC, and substituting the expression for quality factor from here, we can write the Z input impedance, the input impedance ZIN is equals to R by 1 plus 2j Q naught delta omega by omega naught. So we have now the input impedance in terms of the quality factor and resistance. Um, and when this R becomes infinite, if this becomes this R becomes infinite, this the input impedance will reduce to a term like this. So this yeah, so this is something where just in case this becomes an open circuit thing over here. Now, to find out the half power fractional bandwidth, okay, so I was talking about this particular plot over here. If you recall, we just saw some time ago that if we plot the this Z input impedance versus this input impedance versus omega for series resonant circuit, it was something like this, and for parallel circuit, it is just the opposite. But again, this thing peaks over here and at R, and the half power bandwidth will happen when ZIN is equals to R square by 2, as opposed to when this for series resonant circuit it happened for 2 R square, right? But yeah, so if you calculate this bandwidth, if you and try to simplify the term, so from here and here, then you all you need to do is just take mod of this term over here and substitute take mod over here, substitute r by r square by 2 over here, and things would cancel, and you'll get the result. So the bandwidth will turn out to be 1 by q naught. So this is same, but this although the circuit changed and this plot changed, but the bandwidth comes out to be same as in case of the series resonance case. So I'll just pause over here, let you maybe if you want to go through this math over here, and if you are not able to follow any step, we can discuss and let you go through the slide. Please let me know if you find something something which you are not able to follow. Okay, so all the things are very same for series and parallel resonance circuits. Just this the expression for the input impedance changes, but all the relationships since like the relationship between power, voltage, current, um, im- and the relationship with the input impedance, this input impedance term over here, since that remains same, so the other expressions are same. So only when you substitute the value of the expression for input impedance, you find different expressions for the power, voltage, and everything for the two circuits. And uh, this is good that we have the same expression for bandwidth in case of series or parallel. Much easier to remember. So a few more slides on the quality factor, the loaded and unloaded queue. So we have like we have already discussed things about this quality factor. So if you look at, so this is a circuit, right? We have a circuit something like this. So we have a resonant circuit over here, and then we have some load over here. So this, but if you just look at the quality factor of this resonant circuit, it is called Q naught. We call it that as, and this Q naught is your unloaded Q. And if you take the quality factor of this entire circuit, it is Q, and this is called the loaded Q. So, very simple words, this is it. And we will see the relationship between the loaded and unloaded Q. Okay, so in practice, however, the resonant circuit is invariably coupled to other circuitry. So yeah, you cannot just have the resonant circuit. You will need to so it will you will end up having this resonant circuit attached to others, connected to other parts of the circuit, others the components of the circuits, and this those circuits will eventually affect the quality factor of your resonant circuit. And so that is the loaded queue. And we also, okay, so loaded queue is denoted by QL or just plain Q. And let's just take an example where we have this RL load attached to the RLC circuit. So in case of series RLC circuit, this RL will add to the effective resistance. So if you remember how the circuit looked like, so we had inductor and then capacitor, and then there is this RL over here. This is your load resistance. So this RL will be in series with this R over here, and this essentially means the total R will be R plus RL, the total resistance. And in case of parallel RLC circuit, this RL will be in parallel with this R. So if you have this R L C, and then there is another RL over here. So this RL will be in parallel with this R. So we will have the effective resistance will be uh, 1 by R plus 1 by RL. Yeah. So simplifying it, we'll get R into RL divided by R plus RL. So we have found out the effective resistance for the case of series RLC circuit and parallel RLC circuit. And if we define an external QE, so we are defining another this quality factor term, which is the QE. So now we have Q naught of this Q naught of as the quality factor of the resonant circuit, and external quality factor QE for the external circuitry. Okay, and the total quality factor is QL or Q. So the quality factor for the external circuit will be omega naught L by RL, and for parallel circuit, for this is for the series circuit, and for the parallel circuit it will be RL by omega naught L. Or you can also express this terms using capacitor or also. So don't worry. So I'll leave this mathematics to you. So this is very straightforward, and so once you have found out the external quality factor, the loaded Q can be generally expressed as 1 by QL equal to 1 by QE plus 1 by Q naught. And so this is an exercise to verify. Okay, maybe I'll just give this an assignment to verify this. I'm trying to write verify over it. Yeah. So so this particular expression will hold for both a series and parallel circuits. If you define you find out the external quality factor, uh, and you know the quality factor of your resonant circuit and the quality factor of your total circuit, which is the loaded circuit. So this particular thing will hold. So very intuitively, if you see, once you have found out the external quality factor for the series circuit, the resistance is in the denominator, and for the parallel circuit, the resistance is in the numerator. And hence, so if you try to find out the quality factor, so for the parallel circuit, this will be the RL will come on the numerator. Sorry, the RL will, if you are writing 1 by QE, the RL will come in denominator for parallel circuits, and for series circuits, since it is denominator, this will come in the numerator. And for Q naught, you know that the resistance is in numerator, and for QL also. So this will simplify. So I will leave this up to you uh, to solve this as an assignment. Okay. So so we'll move forward. Since I'm leaving this assignment, maybe we can discuss this in a later class if you find difficulty in finding the external quality factor from this observation to this what is given over here. Okay, so this table is also present in Podzar. I'm keeping this over here for your quick reference if you are going to the slides and you want things listed down. So all the important results that we discussed in the class, for example, the input admittance and impedance, power loss, stored magnetic energy. So this is same. Over here, the resonant frequency same, the loaded and external Q for both of them. So a very important chart. I will like you can keep this while solving problems. Now coming to transmission line resonators. So so this thing we have discussed quite a few times, that ideal lumped element circuits are unattainable at microwave frequencies, because at microwave frequencies the lambda is very small, and for your components you will definitely experience phase change, and so it is difficult to design lumped elements at those frequencies. So what we do is we use distributed elements, for example, transmission lines, for the design of our circuit. And we have seen these use of transmission line sections of various length and terminations to form resonators. So So we'll see that now. So transmission line sections can be used for a number of things. So we are already familiar with the uh, knowledge of standing wave. So this is something similar on the similar lines. And since we are looking at the quality factor for these resonators, we will consider this transmission lines with losses. So in our previous derivations, we had RLC, right? So if you consider ideal transmission line, they only have inductance and capacitance, and we assume this R to be zero. So, but in this case, since we are calculating Q, will need to have this. So having resist, so for keeping the resistance, we are introducing losses in the transmission lines, and this eventually means that we have attenuation constant non-zero alpha. So let's take our first example, short-circuited lambda by 2 line. So this we have this circuit over here, and this particular length is equals to lambda by 2 for whatever frequency or wavelength we are looking at. So this length is equal to lambda by 2, and the characteristic impedance is Z naught, the propagation constant is beta, and the attenuation constant is alpha. Since this is having losses, alpha is non-zero. And so for this particular this transmission line section, we can write the input impedance at over here as Z naught tan H alpha plus J beta L. So this is something that we have already derived. And using the identity for hyperbolic tangent, so we have tan H over here because we have alpha over here. So if there was no alpha, this would have simplified to just J tan beta L. But we have alpha over here, and just using this identity, uh, we uh, we have this expression over here. So we have tan H alpha L, tan beta L, tan beta L, and tan H alpha L over here. Okay. So you have to note, yeah, just as we discussed, if this was a lossless line, alpha was zero, then this would have simplified to this expression, which we have been using earlier. Now, so in practice, since the transmission is usually low loss, the alpha L is much smaller than 1, and so we can assume. Yes, excuse me. So we can assume we can approximate tan H alpha L equals to just alpha L. Okay. So for small values, tan H, the input of the tan H, this becomes very linear. So using this and then substituting, so omega naught is our resonant frequency, and delta omega is much smaller than omega naught. Uh, we we can write this beta L expression as omega L by Vp, and then substituting omega by omega naught plus delta omega, we have this expression over here. Now they will Vp is the phase velocity of the transmission line, and also since this length is equals to lambda by 2, we this is the lambda by 2 short circuited line, and we can write this as pi Vp by omega naught. So we're just substituting the this lambda in terms of the velocity and frequency for omega equal to omega naught. We can write this this whole thing will simplify to pi, and this term will simplify to pi by omega naught. So come from here to here by using L equal to pi by 2, and yeah, so now we have beta L is as pi plus delta omega by omega naught, and so we can write tan beta L as tan, and inside the argument we have pi plus delta omega pi by omega naught, and this pi shift in tan does not affect the tangent value. So we know this that tan is periodic by pi. So if you remember, I think tan has some plot like this going on, right? something like this. So this is pi periodic, and yeah. So we effectively have tan beta L, and at for small values, since this delta omega by omega naught, this is very small. So and tan is very linear for small values. So this will become the argument will become this whole thing will be equal to the argument itself, approximately delta omega by pi omega naught. So we have tan beta L as this term over here, and tan H alpha L as alpha L. And using these two observations over here, this observation over here and this observation over here, um, we can simplify the input impedance as this term over here. The Z naught times alpha L plus J delta omega pi by omega naught, since this entire term is much, much smaller than 1. So this term we are ignoring, and this becomes very simple. So the input impedance is now expressed in terms of the characteristic impedance, the attenuation constant, the length of the transmission line, and the delta omega and the resonant frequency. Now, this if you look closely, this equation Zin is equals to Z naught alpha L plus J delta omega pi by omega naught is of the form Zin equals to R plus 2JL delta omega, which is the input impedance of a series RLC resonant circuit. So we just saw this in the beginning of the class, and the last class we discussed this. So this is the input impedance for a series RLC resonant circuit, and this is the input impedance for a short circuit lambda by 2 line. So we have one real part and one imaginary part over here, which of the similar form. So we can now use this. We can compare these two to find out the resistance for a short circuit lambda by 2 line, which is found to be Z naught alpha L, and we can find out the inductance from over here, which is equivalent to Z naught pi by 2 omega naught, and we had the expression, right, omega naught is equals to 1 by root over LC, right? We can use this to find out uh, the capacitance as well. So we have now R, L, and C for this particular short circuit lambda by 2 line. So this particular resonator can be just made equal to this simple circuit that we already had, right? So and the resonator resonates for delta omega equals to 0, and the input impedance at that particular. So if we make this delta omega equal to 0, that is when omega is becomes equal to omega naught. So at that case, the imaginary part becomes 0, and we see resonance, and the input impedance is again now equal to resistance, which is equal to Z naught alpha L. And if you look closely, this particular resonance will happen for all values of L equals to n lambda by 2, for n equal to 1, 2, 3, and so on. And the voltage distribution can be given like this. So if for n equal to 1, we have short circuit over here, and we have the short circuit over here. So we see one full fraction. Similarly, this can happen for n equal to 2, or n equal to 3, and so on. So we can see that we can have this resonance at multiples of this n. And the quality factor is given by omega naught L by R, and we can substitute the value of L and R over here, and this turns out to be beta by 2 alpha. So any questions from the short circuited lambda by 2 line? So this is what we were referring to when we were looking at the series RLC circuit. So series RLC circuit is the short circuited lambda by 2 line is the equivalent of yes, series RLC circuit. Okay, so we'll move to the next topic. Okay, so one thing that I think I missed this. So this result shows that the quality factor decreases with the attenuation of the line increases. So if you look closely, this the quality factor is given by beta by 2 alpha, and if you increase the attenuation constant of the line, the quality factor will decrease, which is same as what happens if you increase the resistance in case of series RLC circuit. The quality factor decreases if you increase the resistance. Similarly, if you increase the attenuation over here, which also means loss, same as for resistance, so the quality factor reduces. Okay, now looking at short circuited lambda by 4 line. So it will the math is very similar. So we find out the input impedance for lambda by 4 line over here. Like this, we can go through this mathematics. So we have the tan h thing over here. We simplify this, and instead of using just tan h now over here, we change this. Instead of using tan beta L, we are writing cot beta L for lambda by 4 values, and again we calculate the beta L value for at lambda by 4, and substitute omega equal to omega naught, and this sorry so this lambda by 4 is at omega naught, and we substitute omega by omega naught plus delta omega. Omega naught is the resonance frequency, and we do the same things. Now we are, since we are expressing in cot over here, we find out the cot beta L value, and this and finally find out the input impedance. So the steps are similar. So again, we are calculating the input impedance using, and we are using the tan h formula since we have alpha over here. We changed instead of using tan beta L, we used cot beta L, and found out the beta L value for L equal to lambda by 4. Uh, Once we had the beta L value, we found out cot beta L value, which came out to be this value over here. And tan h alpha L for small values can be written as alpha L. And using this, we just substitute tan alpha L and this cot beta L over here to get the input impedance as Z naught by alpha L plus J pi delta omega by 2 omega naught. Now, and this is happening because this term over here is much smaller than this alpha L term. Sorry. So this term over here is much smaller than 1. And so we are ignoring this, and we have Z naught by this entire thing. So in this, and if you look closely, this particular result is same for as we found out the input impedance for parallel RLC circuit. So for parallel RLC circuit, the input impedance was given by Zn equals to 1 by R plus 2 J delta omega C. And to compare this thing to this thing, we see that this R is given by Z naught by alpha L. The capacitance is given by pi by 4 pi omega naught. This capacitance, we compare it with this term over here, resistance with this term over here, and we can find out the inductance if you have the value of capacitance. Okay, so I'll let you read this because this is same as what we did for lambda by 2 line. And please let me know if you find any difficulties, any of these steps. Then we'll proceed. Okay. So we had the length of the transmission line. We tried to find out the input impedance, For doing that, we had this tan H term, tan beta L term. This tan beta L term, we changed it to cot beta L term. Then we simplified this beta L term, the argument for the two things. So for this argument and this argument, we simplified them, we put their values, found out the input impedance, and then we realized this is very same as the parallel resonance circuit. And then on comparing, we found out the equivalent, the resistance for the equivalent circuit, the capacitance for the equivalent circuit, and the inductance for the equivalent circuit. Now, for a short, so yeah, for short circuit lambda by 4 line, if you like this is the circuit like this. So if for short from this observation over here, once we had the input impedance and we compared it to the parallel thing, we see that this has a parallel type resonance as compared to when we had the lambda by 2 line, where we had series type series, and for lambda by 4 we have the parallel type resonance. And the and at the resonance frequency, right? So when we have delta omega equal to 0, when delta omega is equal to 0, the imaginary term goes away, and we have only the real part with us. And similar to a parallel type resonance, the input impedance will become to the resistance, which is equal to Z naught by alpha L, and the equality factor is given by omega naught RC. And if you substitute the value of R and C from here, we find that this equality factor is again equal to beta by 2 alpha L, which is similar to what we saw in the previous case as well, for lambda by 2 as well. Okay, so any questions from here? Okay. So we've seen short circuited lambda by 2 line and short circuited lambda by 4 line. Now let's look at open circuited lambda by 2 line. So it's often we we cannot have a short circuited lambda by short circuited lines, right, on the circuit, because for example, if you are familiar with PCBs and microstrip lines, so for example, if you have a microstrip line like this, and if you want to short circuit it, you'll have to make a via over here and plate it through hole, and so that you can get the short circuit over here, or so something like that. Or for example, if you have a PCB over here, and there is this transmission line and this branches into this line over here, and you want a short circuited point over here, then you'll have to do a via. So instead of doing that, we can also have open circuited uh, transmission line, right, where you end up an open circuit and you don't have to do anything. So open circuited transmission line, this is more convenient for fabrication perspective. So we often use open circuited transmission lines. Now this is the example, like equivalent, like simplified circuit for a transmission line system, and we have the input impedance as Z naught, propagation constant beta, and attenuation constant alpha. Again, since we are looking at quality factor, and that this requires us to have resistance, which is actually loss, and loss in case of transmission line is given by attenuation constant. And now this length L is equals to lambda by 2 at omega naught at the resonance frequency. So if you from previous observations, if we have a resonance over here, so we can have this resonance something like this, or this which is given over here. So for open circuit, basically we have but when we had the short circuit case over here, so the voltage reduced to 0 at the short circuit. Since it is open circuit, the voltage will be at the maximum. So for the resonance case, this become the wave comes over here and reflects from here and goes back over here. or if waves comes over here as a higher harmonic, reaches the maximum and then reflects back from the maximum and then retraces over here. So we are performing the standing wave like this. If you are able to follow the pointer, okay. So similarly, again will solve we'll calculate the input impedance. So input impedance will be given for an open circuit lossy transmission line as cot H alpha plus J beta L. So you can refer to the previous notes for these expressions. And when we try to using the expression for the cot H hyperbolic, which has a complex argument, um, we expand it to this form. We have tan beta L, tan H alpha L, and we already know that this alpha L is very small, so we can simplify this thing to just alpha L. Tan beta L can be again simplified further for lambda by 2 line. Then we have already seen this, right? So this from the short circuited lambda by 2 line, the beta L is simplified to this form over here. And when we had beta L and tan alpha L simplified to these expressions over here, we just substitute them back into this input impedance thing. And the input impedance looks something like this: Z naught by alpha L plus J delta omega pi by omega naught. So, and this again looks familiar. This is similar to the input impedance. Yeah. So this is the input impedance for this circuit, for open circuited uh, transmission line, lambda by 2 length. And this is the input impedance for a parallel RLC circuit. So if you compare these two, this is, you can find out the value of the resistance of the equivalent circuit. So this particular open circuited line works as a parallel resonant circuit, which has RLC in like parallel RLC. So and if you compare, if you just divide this Z naught over like this, Z naught over here, and similarly if you divide this R over here, you can compare, and we find that this R is equals to Z naught by alpha L. Capacitance is equals to pi by 2 omega naught Z naught, and the inductance can be found out using the omega naught equal to root over LC. So we from the capacitance we can find out the inductance, and the unloaded Q is given by omega naught RC, which again simplifies to beta by 2 alpha, same as the previous two cases. So that's all that we have planned to cover today, and this is the end of the module 7, I believe. The resonant microwave resonators. So we looked at the series RLC circuit, parallel RLC circuit, and transmission line resonators of short circuited lambda by 2 length, short circuited lambda by 4 length, and open circuited lambda by 2 length. They simplified, and their equivalent circuit was simplified to the series and parallel RLC circuit that we had already discussed. So, if any questions from the what we discussed now or whatever we discussed from today? Otherwise, we'll close this class for today, and I'll try to take a class on Saturday and Sunday both, so that we can like quickly wrap up this particular course. We lost a few classes in the middle. Yeah. Any questions from here? These all the Smith chart things were discussed from Cheng, and this transmission and resonator is again covered from we switched back to Podzar, and all these things have been covered from Podzar. You can refer to the textbook. It is written very beautifully by Podzar and a lot of details. I've tried to concise them in the slides and walk you through the steps. And you can try solving the questions as well. So initially we have not covered the perturbation method, which is required to which is used to calculate the attenuation constant. You can refer to the earlier chapters to know the perturbation method, and using based on that, once you have the alpha, you can there are some questions in Podzar which use that information to find out the quality factor for these microwave resonators. You can look at the examples. And let me know if you find any questions or queries, if you have or you're facing any difficulties. So we covered parallel resonant circuit, loaded and unloaded Q, and transmission and resonators, and this marks the end of this module. The next class will start with power dividers and directional couplers. Yeah, so that's it for today. If you don't have any questions, we can end now. Okay, maybe I'll stop the recording now. Okay, thanks guys. Thanks for joining.